In this simulation, we have a spacecraft whose job it is to point its third axis, its z-axis, right at a ground location. In this case, we can use Boulder. So that's what we want to do. And there's two new modules in particular that we'll be talking about. Ground location, which will always put out an output message telling us where is Boulder at this moment, even if the Earth is rotating. And location pointing, which will be nice because that gives us that's a feedback control law that will tell us the guidance of, well, this is where I am pointing and I should be aiming down here. How should I be controlling my attitude? What's my tracking error and how do I provide the proper guidance? So we'll be talking about those two modules. And then the output, you should see your attitude tracking errors converge to 0 and the control torques go to 0. Everything is normal. Well, let's look at the Python code. Again, single process, single task. I'm running for 20 minutes. I'm running at 1 Hertz in this simulation. And I'm creating a spacecraft. I'm creating Earth. No spice. So Earth is actually just going to be at the origin with no translation and no rotation rate. You will see that in the visualization. If I would have made spice control the Earth position, it would actually rotate underneath me. But we're not doing that in this particular scenario. I add Earth to the spacecraft, all pretty much standard stuff. I set up initial position, initial attitude, and rates. I'm setting up an external control module. So this will drive the attitude with a control torque, an external control torque. Simple nav gives me my estimate, where do I think I'm pointing, like a star tracker, and where am I, my onboard ephemeris. Now we get into the new stuff. So ground location, this is a module. So let's go search for that one. Or actually, I think it's already here. Yeah, I've got a link. This ground location, its purpose is you can specify on a body a certain location, either in Latin long or just direct in XYZ coordinates if you want. And it will then take that body's, like Earth's position and orientation, and compute where in space is this location, like Boulder. We want to talk to Boulder. Pretend you're aiming a communication antenna, for example, to talk back to Boulder. You want to aim at it. So there's different ways you can set these up. There's a planet input message, like with hill pointing. This is an optional one. If you don't connect it, it assumes the planet's at the origin at 000 in locations. But if that's not the case, then you do need to specify an input message if the orientation or position is different. So here we're not going to use it. Actually, there's no spice. There's just that Earth at the origin lined up with the inertial frame. Spacecraft state in messages. You can see with this lettering, you know right away this is a vector of input messages. So we can have this will not just create the location and access message relative to one spacecraft, but you can do multiple ones. So you don't have to make, if you have 10 spacecraft and you worry about do they have access to Boulder, you don't have to make 10 modules here. You can just add spacecraft to the same module. And you do that with this method, add spacecraft to model. And then it will create a vector of output messages. These are the output access message. This is the current ground state out. There's a single ground station in this one only, but multiple spacecraft. And it will give you the output message specifying where is the location relative to inertial or location relative to the planet in the inertial frame. Those are our two. The access message payload tells you, has it got access? So it does more than just tell you where is the space, where is this location, Boulder. With the spacecraft stuff added, it'll actually tell you, does the spacecraft, is it above Boulder? And if yes, what happens? And in the visualization, you will see an access line being drawn when it has access. There's a slant range you can specify, an elevation you can specify. That will actually be computed in this output message. There's an azimuth angle for the spacecraft, range dot, L dot, elevation rate, range rate, and azimuth rate. But in particular, it also gives the spacecraft location relative to the ground location. So spacecraft relative to Boulder in south, east, and z-axis, up axis. And it also gives the velocity, the time derivative of this vector, those components. So it does actually quite a bit. And we're only going to use part of it here. We'll need to know where is the location of that spacecraft. So we've got that now set up. So here we do specify, for example, a planet radius. We specify a location in Latin long and an altitude as well. So that's kind of what it needs to know. The planet radius is important to figure out if the spacecraft has access. Is it over the local horizon or not? So it needs to know that. It needs to know the minimum elevation. So it has to be, the spacecraft would have to be at least 10 degrees above the local horizon from Boulder to be visible. And you can also specify a maximum range. If you don't specify this, it assumes you have infinite range from the communication. But if it has a maximum range, let's say this radar or this communication dish only can talk for this distance, that'll actually be visualized, and that's taken into account into, do you have access? Are you within that range? Then we add that spacecraft to the module, so it will compute all this stuff and compute it. So it's good. Next one is we need a new control module, and that's called location pointing. So if we go back here, that's the second new one, location pointing. Essentially, all the math is down here. It takes our location of the satellite that we want to care about relative to the satellite. What's that relative position between the spacecraft and Boulder, essentially? From that, there's a p hat vector. That is the vector in the body frame, like the z-axis. Maybe that's your communication axis direction. You want to line up your z-axis to point at Boulder. So I'm doing that with a cross product, find an eigenaxis rotation that will drive me there. So it's really 2 degree of freedom control. I'm not controlling a 3-dimensional reference frame. I'm just doing a 2 degree of free reference frame here. There's also an optional argument that you can set. That's specified down here. There we go, use bore side rate damping. So while pointing an axis at Boulder still leaves this degree of freedom open, that'll be the case. It'll just settle to whatever came naturally. If this flag, use bore side damping, is off, which it is by default, then it allows it actually to slowly rotate. It doesn't damp those rates in the control. That's good if you're just doing safe mode, for example, or something pointing at the sun. You want your solar panels pointing at the sun, getting powered. You don't care if you're rotating about the bore side slowly. That's okay. You don't want to waste effort. But here for imaging, for example, looking at Boulder, if you are doing an image of Boulder, you don't want to be rotating while you're looking at Boulder because you would cause some extra smearing. So we're going to set that one to 1, actually, in our module. So you can read more on that module if you wish. So that location pointing, let's see, where were we? Down here. We're setting it up, that use bore side damping, we're setting to 1. So we should do 3-dimensional rate damping, but 2D attitude control. We're specifying 001 as the p hat, so that's the body fixed vector that we need to line up to point at Boulder, in this case, the z-axis. The attitude in subscribes to simple nav out, that makes sense. Bore side is set, spacecraft translation in connects to simple nav translation out, that should make sense too. And then the location in message, this is where we need to know where is Boulder. We're going to connect to the ground station, which models Boulder, and there's the current ground state out message. So that's the one that had that thing. We don't need the access out message in this simulation, actually. We'll use it in the visualization, you will see, but we only needed 1 for the location pointing. Now, let's go back to this location pointing code. There's several output messages, actually. There's 2 in particular. One's called attitude guidance out, because in the end, what we really compute is sigma b relative to r. And we do a numerical derivative to get omega b relative to r. And then that becomes our attitude guidance. That guidance could drive MRP feedback directly. And that's what we'll do in this simulation. In other scenarios, since we know sigma bn and we know sigma br with the right attitude math, we can compute sigma rn, the reference state, at this instant. And that is done as well. So that's provided as a second output message, attitude ref out. This is the input that's needed, for example, if you want to use attitude tracking error. Attitude tracking error is nice because you can also, in other words, driving B to R, you could do alternate body frames, or maybe there's complex code where lots of different flight software stacks like safe mode and sun pointing and hill pointing and boulder pointing and science pointing and whatever you have all combined to attitude tracking error. You don't want one oddball just getting directly the guidance. So we put out both guidance message and a reference message, and you can use whatever you wish, whatever makes sense in your simulation. So yeah, so that now we've got all this done. So now here we do MRP feedback. There's no attitude tracking error because we're going to use the guidance directly. And you can see the guidance in message subscribes to location out attitude guidance out message. So we're using the Sigma BR guidance message directly. And that will drive us to point the spacecraft z-axis at Boulder as we fly overhead. And that will be, time varying. The rest of it, the control torque of the MRP gets directly connected to the external force torque model again. We set up recorders, the vehicle config data. There's a variety of simulation that we can run. For the visualization, I'm actually setting it up to show Boulder as a location. So you will see this pink cone coming from the Earth. And also it illustrates, are we in sight? Actually, Wizard will highlight that. And I'm specifying some other things that it's going to show here. So anyway, so we'll look at Wizard in a moment. But in this case, if I'm running it from the command line, let me go here, Python 3 scenario at location point. It should run, and you can see our rate tracking errors go to 0, control torques go to close to 0. Attitude errors converge, it's getting asymptotic again, pretty close to 0. So that's good, right? So those are the plots. If you uncomment this line and then run it again, you would actually save off a Wizard binary file, and I've already loaded it up here. So, whoa, what happened to my binary? Okay, just a second. Well, that did not like it. Load this up again. And there's the attitude location pointing, and it's going to run. So cool. So now you can see, I'm going to stop this here for a second, turn on the light. There we go. It's because we're kind of in the dark area. We start up here. So we actually get over Boulder. You see the spacecraft rotate. Its z-axis kind of goes normal from the solar panels. So it's pointing its z-axis at Boulder. And as we fly over Boulder, there would be Boulder. It's aiming at Boulder and continues to aim at Boulder. And then it goes outside. That was the access cone. A little bit hard to see in spacecraft local view. So let me double click on the planet. Now you can see actually Boulder on the planet. And you can see the planet doesn't rotate because we just did create Earth. We didn't connect it to Spice. So it's just keeping a constant attitude here, but it doesn't have to be the case, but that's what we chose here. So the spacecraft, you can see it rotates at the beginning. And then as it goes over, it keeps rotating to pointing the z-axis there. And it'll continue to do that. Nothing stops when it doesn't have access anymore. Here we've given it limited range, which means you can see that range highlighted with this cone. If the cone is flat, then you have unlimited range. If you see a bubble on top of it, like an ice cream cone, that's the range that we specified for the ground station. So it's kind of nice. In this scenario, I'm showing you how you can visualize a ground station, and you don't have to make it pink. That's just a color I chose because the dark background, it kind of stood out. So anyway, that was a quick illustration of how we do location pointing in space. One final thought, we connected a ground station to the location pointing, but sometimes we don't want to point towards a location. Maybe we want to point towards just the moon or the sun. Let's say you have a science sensor now, or an asteroid, and as you're flying by, I just want to point at that asteroid. So instead of connecting the location in, which has come from a ground location output message, you have another one, an alternative, a cell body in message. So if you have an ephemeris message, where this object is, where is the sun? If I'm supposed to point at the sun, or where's the Earth, or where's Mars? Because you're flying around Mars and you want to point your antenna back at the Earth. You just can connect the Earth's ephemeris message to this module, and it'll point the antenna or the communication dish at Earth. So it's done in a very modular way. We've demonstrated here via a ground location, but you also can actually use the same module to point at a celestial location. Hope you enjoyed.